Hello. Okay, there's no echo. Hello? No? Yes, I'm on mute. Yes, perfect.
Okay, welcome everyone. Today I'm very happy to have Merve Karabulut from College of Engineering and Computer Science, Florida Atlantic University, and she's going to talk about area efficient first order masked modular reduction for ML-DSA in Caliptra Root-of-Trust. Over to you.
Yes. Hello, everyone. Thank you so much for attending this meeting. I'm Merve. I'm doing PhD. This is my third year. I'm working with Dr. Reza Azardarash, which is doing mostly post-quantum cryptography. I guess last year I presented like a presentation about attack on ML-DSA, side channel attack. And then for this presentation is about more of like a side channel countermeasure. So basically how to mitigate such attacks. And we did a design for first order mask for modular reduction in ML-DSA. And then this design was integrated in Caliptra, which is open source root-of-trust subsystem. So before going all the details, I just want to explain what did we do. So right now, quantum computers, they are powerful enough to solve RSA ECC, which is classical cryptographic schemes. And that's why NIST initiated like a PQC standardization process in 2016. We selected algorithm, industry started to use them, and Microsoft, which is like one of the high-tech companies, they started to use this cryptographic algorithm in their chip. And okay, they are resistant quantum computers, but their physical implementation still can leak information. And we perform side channel attack before the countermeasure. They apply countermeasure, but now it caused like a big area overhead as well as latency. And then we are thinking how to optimize that because this chip is going to be used almost everywhere. So I will just give like a little background of what is post-quantum cryptography, why do we need that? And then mostly I will talk about side channel because I guess like one of the last presenter, Bardia, already talked about PQC. But still, right now we have like new advances in quantum computing, like almost many big companies, they're developing their own computers. Google has Google Willow, Microsoft has Majorana, Amazon has own their qubit support, and they have different qubit type to use this like computing faster. So, but the problem is that, okay, they are powerful, they have really good capacity to solve like almost any math problem, but they are also threatening current digital system security because they can also solve math problems in polynomial time. But we use this math problem in cryptography, such as we have RSA ECC, and then the Shor's algorithm saying that this computer can solve this discrete log problems or factoring large integers problem in a polynomial time. So that's why we need to develop new algorithms. So I will go through like a RSA. We are choosing P and Q, multiplying. We have N, and then we are choosing public and private key. And then encryption is like exponentiation. And the hard problem is how to recover the N power E without D. But as we said, this problem can be solved with quantum computers, as well as ECC. It is basically scalar multiplication can be also threatened by quantum computers. So that's why NIST initiated PQC standardization process. And first, like ML-Chem, ML-DSA, their previous name, Kyber and the lithium, they selected, and then they ran off standardized in NIST documentation, FIPS 203 and 204. And then Falcon is also standardized as a digital signature algorithm. Then we have Sphinx and HQC. HQC is kind of alternative for ML-Chem. It's not widely used, but it's like alternative solution. And then we have Sphinx, which is like a more stateless hash-based digital signature. There's also standardized in FIPS 205. And also industry has started to use them like a AWS launch PQSSH, kind of like a communication protocols, and they added like a post-quantum support with their transfer for SFTP. NVIDIA announces their with Kyber acceleration. HP announces their stateful hash-based signature scheme. Zoom announces their end-to-end PQC encryption. Google that they're using like ML-Chem in Chrome. OpenSSH right now, including ML-Chem. Microsoft is also doing like a many work with PQC. So that's why it is widely used, and industry is also trying to adapt this. So what is ML-DSA? Because we were targeting ML-DSA. ML-DSA being used mostly in industry, but why? Because let's compare with Falcon, like a Falcon, not the standardized algorithm. However, Falcon is working with floating point arithmetic, which is really hard to implement in hardware especially. So that's why they don't want to use in Falcon. It is complex, hard to implement, hard to work, hard to validate. And we also Sphinx, but Sphinx key sizes are really large, as you see. Like I also put a table to like a compare which key that we are using. So signing key, as you see, Falcon has larger key sizes. For verification key, yeah, like comparatively ML-DSA is larger, but the signature size is showing that Sphinx is really high. So since signature size is going to be transferred, and it will be also in the certificate if we are doing this communication, so it is costly for us, because like assigning that much large number is not a good idea. So basically ML-DSA is efficient, it is secure, and also it is easy to implement in hardware as well as in software. So I will go through like what is ML-DSA. ML-DSA using like a model learning with errors and model short integer solution problem that is resistant to quantum capable adversaries. And then these problems are believed to remain hard, even large scale quantum computers. It is operating in a polynomial ring where we have like a modulo Q, which is 8 million something, that I'm not going to say this much number, but we have also the highest coefficient numbers is 256. So ML-DSA has like a key generation, signature generation, and signature verification steps. So this is like an overall flow of key generation, signature generation, verification. What are our values that is working? I try to highlight the secret keys, but I will go through like a more detail. What is the secret operation happening? Which are the values that we need to protect, and how do we attack side channels? How do we attack these values using side channels? So first we are generating keys. Idea is that first generate a vectors S1, S2. We have basically like some kind of random generators and then sampling algorithm. We are giving the seed and we can generate S1 and S2. The idea is that let's generate public value T. T will be A multiply S plus S2. So even we know S1, so let's say that T, there is no S2. If T equals A multiply with S1, A is public, T is public, we can find the S1. But if we add this secret value additional S2, we are basically covering S1. So this is how we are generating keys. So we are generating matrix A, we are generating sample secret vectors S1, S2, we are computing T, and then T has two values, T0, T1. High bits is going to be in the public key T1, and then T0 is a secret key, but in FIPS documentation, they didn't, no.
You haven't shared your slide.
Oh, okay, on my bed. Sure. Is it good that they can see right now?
Oh, yeah.
Okay, perfect. Let me just do this and then.
We not was showing before, but now it's not showing.
Okay, let me try one more time then. I just wanted to get rid of that. It's good. Okay, perfect, perfect. So we have T1, T0. T0, they say secret key, but in FIPS documentation, they clearly said that T0 can recover. Since T is public value, T1 is public value, we can also recover T0. And then we have like encoding function to like compress this public and secret key, because that's the public key that will be transferred in the digital system. So we have like an encoding algorithm. And then for signature generation, idea is that, okay, I have message, but I want to make sure the other receiver that the message is coming from authorized user. So I'm saying that this message is coming from me. So I'm signing with my secret key. I'm sending my message and my signature, and the other user can verify this message using their public key. And we have input, secret key message, and some random numbers. We are expanding the private key. We are recovering the private key. And then we have this. First, we are sampling a random mask Y, and we are generating W by multiplying A and Y. And we have other value W1. This W1 will be in the challenge C. And then we are computing Z, which is also a part of the signature. This is the core operation kinda. We have challenge Y, public value challenge C, and S1, which is like a basically manipulation of C is coming from message, S1 is already secret key, we have this computation, and it is giving our signature. It's like some kind of mathematical, like a magic that is happening. But I'm not going to go on that much detail of math part. I will talk about more implementation. So that's why I'm not giving that much core, like operation, what's happening. But the problem is that the Z can be like a really big. We don't want to have like that much big signature. So we have kind of loop. We are, if Z is too big, it's not like out of the boundaries, we are rejecting and trying to calculate again. So for verification part, right now, we don't have any secret values because it is from VR receiver part. We don't need any secret values that to deal with. We have public key, signature is also public. We have like, again, computation to get the signature, and we are calculating this signature is the same as the signature that we receive. If it's same, we are saying that accept the signature, accept the message. I trust this user. If not, I don't trust this user. So I'm not going to go that much detail, but I put also like a pseudo code of this like ML-DSA signature generation to like a highlight the operation that we are using. This is taken from like a NIST documentation, FIPS 204. It is basically where we are following when we want to implement anything, because it is giving like a good structure of which function we are going to use, which order we are going to implement, what is our constraint, so that it will be standardized. That is, we are saying that we implement this algorithm by following this documentation. So as you see, there's like an entity that we are seeing almost everywhere. Whenever we are generating S1, S2, T0, and then as you see like a line 12, we have this like a multiplication that is also being happen in entity domain. So entity is widely used. The reason is that, let's say that we are doing multiplication. Think about like elementary school. When we are multiplying two-digit numbers, we are multiplying first digit, then the second one, then we are going the other part, we are multiplying one by one. So if we have two-digit numbers, we are doing 4 multiplication. But this is really high computation. It means that we have n-digit numbers, the complexity is going to be n square. So entity is some kind of operation, some kind of transform that we are using, and then it is reduces to n log n. But since we are using secret operation, it is also a place that is leaking for side channel. I will talk about side channel, but it is just keep in your mind because we are dealing with secret information in this transformation part. So that's why in our attack, we use entity-based point mass multiplication. As well as the keygen and verification was also using entity, but we didn't discover that part. So this is what I explained just before. So while we are doing so-called multiplication, basically each digit will be multiplied with each, which will then we are going to add those numbers, which is n squared. But entity is basically converting these two numbers to entity domain and then doing point mass multiplication, which is like each element is going to be multiplied with each of them. So it is just like a n multiplication instead of that much. But the entity conversion is taking log n, so it is n log n complexity. So we are using ML-DSA almost everywhere, IoT devices, VPN, TLS communication, cloud, and data centers. But this implementation, as I said, vulnerable. There's like a software implementation and hardware implementation. So when I say hardware implementation, think about we have FPGA, where we are basically like building the gates in this FPGA or ASIC design. So it is not like a CPU that is doing all operation. But software, we have like a CPU and then we are programming CPU with this operation. But there's like a many paper and many research that is doing software attacks. Even they're protected. As you see, there's like a fifth order mask implementation of Kyber and there's a still leakage and then they can recover the secret key. So it is easy to attack. So that's why we want to use like a hardware implementation. We want to protect that part. What is Caliptra? Because I was keep saying like that Microsoft is implemented Caliptra, but what is Caliptra? So it is an open source root-of-trust subsystem. So basically, they want to use this chip in their data centers. Because let's say that I'm a remote user, I want to use their cloud server, but I should be authorized to access this center. But I also want to make sure that my operation that I'm running in these servers is secure. So no one tampered. I do trust this data center. So they have like this chip that is responsible for this all security related operation, which is called Caliptra. So it is implemented by Microsoft, but they are going to like work with AMD, Google, NVIDIA. So it is responsible secure boot, attestation, key management in SFC. So first, it is really like a wide content and context. It has like a really huge study because it is like a covering from, they are even don't trust where the chip is produced. So they are starting this security foundation from, let's say that they did this chip in Taiwan, but they don't also trust Taiwan. Maybe they are putting something that they can read information. So they don't trust Taiwan. They don't trust the supply chain that is coming this chip. They don't trust who is the programming this chip. And then they don't also trust the user is using. So that's why it is like a multiple verification process is happening. So it is responsible. That's why it is secure boot. Secure boot is basically when we are powering this chip, we want to make sure that everything is validated, everything is authorized. Yes.
What have like digital signature there on ML-DSA, not
Yeah, that's really good question because actually it is not updated figure. Right now they also implemented ML-CAM in their accelerators, but when we were doing the study, that there was an ML-CAM. Like ML-CAM is they just implemented, I guess, last month. So I should have included, but they have this like a cryptographic subsystem, which is called Adams Bridge. And ML-DSA were the PQC part. The other one is more classical cryptographic schemes and symmetrical, which they also like I have AES, they have SHA algorithms, they have also ECC. But we are focusing on ML-DSA. So they name this like a cryptographic subsystem, Adams Bridge. It is really good for like researchers like me because they did open source, they documented everything they have done, and there's not that much hardware implementation you can find when it comes to PQC. So they design this accelerator who's doing key generation, verification, signature generation. So each firmware is signed by ML-DSA, and the Caliptra is verifying the signature as well. So what is side channel attacks? So side channel attacks is basically very kind of new study. It's not like 1,000 or 100 years. It is just started in 1999. There's a vet called Paul Kosher. He was into cryptography. He wanted to learn like what else we can do to attack these schemes. So he attacked a smart card, and this smart card was using DAS. He just like listened the power usage of this smart card without knowing what's happening, without knowing any secret key, and then he was able to extract the secret key. So he discovered this side channel attack, and then the other researchers trying to find like other things. So we have physical and architectural side channel attacks, which I will be talking about physical, which is like a physical, we are listening to physical environment of this chip or device to extract the secret key, that we can use power, EM, or even acoustic noise of this chip. There's also a microarchitectural side channel attack, which is more of computer science people job that I'm not going to go over that much detail. I will talk about power side channel attack. So idea is that attacker come into this room, he has access to the room and like where this cryptographic operation happening in this chip. So he doesn't know what the chip is doing, but he can trigger the chip that is doing the cryptographic operation. It is easy. We said that secure boot. He will just power on the device that will do cryptographic operation to secure boot. So he also knows that which algorithm is being used because it's already publicly known, because everyone should declare which algorithm they are using. Microsoft said that I'm using ML-DSA. So the attacker can send a plain text, which is basically running, sending a firmware, and then started to listen to this physical information. It can be power, so it will basically put like a glitch, not a glitch, but kind of resistor in the power supply, and then to measure the voltage changes of this resistor, and then understand how many voltage is being used during this cryptographic operation happening. So we say that we need to have physical access in our threat model. We have control over the inputs. It means that I can send different firmware because I want to have like as many as power traces that I can do also statistical analysis. I need to have some kind of measurement. I said that I should have access to power supply, which is probably possible. And then I have like a leakage modeling that I will do the statistical analysis, which I will explain later. And then I extract the secret key. So we have non-profile and profile attack. Non-profile attack that I said that we are accessing the room and we are just collecting power traces and then doing some kind of statistical analysis. And profile attacks that the researchers are trying to find a way to use machine learning methods. So idea is that I'm doing this operation at my home because I know that which device they're using. I'm collecting my power traces with different like inputs. Then I'm like trying to understand what could be the secret key by training a model. So what's the like a machine learning model? We have different inputs and we can understand by this input what will be output. So this is profile attack, but I'm targeting for non-profile attack because the profiling attack, the idea is kind of more complex. The assumption is too wide. They should have the exactly same device, which is not the possible case. It is always not the possible case because they can say that we are using ML-DSA, but they don't need to say that we are using this device. And each device has their own characteristic of like a power supply. So what is power side channel attack? We have CMOS, PMOS, we have like a dynamic power usage. So let's say that we have bit 1 and bit 0. So if you want to make bit 1, we need to give like a 5 voltage to increase the CMOS and then make it 1. And if you want to make it 0, we need to lower the power supply so that it is 0. So it means that we know the data by kind of changing this value. So the idea is coming from there. So as I said, we have this crypto engine. We are putting like a shunt resistor, and it is draws to varying current depending the data being processed. So if it is 1, it is high, it is 0, it is low. Then I have oscilloscope to understand what is the value. So this is the first simple Powell analysis. It is coming from RSA. So RSA has this square and multiply algorithm, because if you remember, I was saying that in encryption decryption they are getting power of E, power of D. So this power operation is really hard operation. So they have this square and multiply algorithm that they develop. So they are converting this exponent to binary formation, and then they are checking each bit. If it is 1, they are multiplying, and they are also doing square. If it's 0, they are just doing square operation. And then one guy, he was like, okay, let me see the power trace. And they realized that if it is 1, as you see, it has like a small voltage and also big voltage. It is square and multiply. When it is 0, it is just square. So you can clearly understand, just looking at the power trace, what data is being processed. Since its exponent value was secret key, it means that I extract the secret key. So it is coming from this idea. This is very a fundamental example, but to just understand what's happening. But we have some limitation. So simple power analysis, okay, we just look at the power trace, you understand 1 and 0, but it's not always, multiply and square. We have like big numbers, we are doing complex operation, so it is not easy way to attack. Then the researchers developed a couple of statistical analysis. One of them was DPA, differential power analysis, which is basically collecting many power traces and then understanding, when the bit was 1, it was similar to this. It was 0, it was similar to this, and then they're applying some statistical operation. Where the correlation power analysis, which is widely used because it is easy to attack for large numbers. We are sending plain texts, or we can also just collect the ciphertext. It doesn't matter where you attack, collecting power traces. And then there's like a well-known Pearson correlation formula where we are calculating the weight model and also power traces. And then this formula is giving us Pearson correlation, and the highest Pearson correlation, it means that correct secret key. But I was saying that leakage model and then like Hamming weight, Hamming distance, what are those? So there's two leakage model, Hamming distance and Hamming weight. Hamming weight, basically how many bits is 1 in this number. So as you see, 1, 0, 1, 0, it has 2. Hamming distance is saying that, so I'm trying to understand, so in the digital design, we have registered the value in one clock cycle, it's something else, the other clock, it's something else. To change this value, I'm giving like some power voltage. So I'm just calculating the distance, Hamming distance between these two numbers. It is basically, let's see, first number is 1, 0, 1, 1, which is 3 bits are 1. And the second number, it is 1, 0, 0, 1. I'm sorry, 0, 1, 1, 0. So it is two numbers are 1. So basically XORing this value, and we are saying that 3-bit change. So this is also giving how many power is being used.
This thing is a bit reminiscent. First thing is a bit reminiscent of inner analysis, where basically you're doing full sum of the sum of the bits. And the second one is reminiscent of the differential analysis.
Oh, I'm not familiar with that part. I'm just saying that how many bit is changed. How many bit was 0 and how many bit is changed to 1, or for example, let's see the first bit. First bit was 1 and it becomes 0. So it means that it changed. The second bit was 0, it became 1, and the second bit changed also. Third one was 1 to 1, so it didn't change. So it means that I didn't need to give that much power supply. I'm just keeping same. But the last one's also changed. So I have 3 changes. So that's why just Hamming distance is 3. So the idea is that let's collect power measurement and then trying to understand where there's a correlation between this model and the power consumption. And okay, that's a good idea, but it's not a good idea to attack without knowing whether it is leaking, because maybe they already have such channel protection. So there's like a test where we say t-test. We are sending 2 sets I'm just sending this device 0, or I'm just sending random numbers. And if there's like a distinguishable power traces, it means that, okay, this is leaking, because device is giving predictable answer because it is changing based on the input. So idea is that it shouldn't be changed. So t-test is giving this analysis. So the t-test that we apply for TVLA for Caliptra before protected version, we saw that TVLA has like some value. It should be -5 to 5, actually 4.5, and it was clearly leaking, and it was higher than the threshold that is showing that it was leaking. And then I will talk about how this implementation happened. So we have key generation, signature generation. We said that they are the sensitive because they are operation secret key, which is vulnerable to side channel attacks because they are processing secret information that I can understand, applying some statistical context. But key generation was also, I was like mostly talking about signature generation, but key generation is also using like a secret information. But in digital design, like in digital system or like communication protocols, we don't do key generation that much often. So we are generating keys for one time, and then we are using for almost like let's say that 100 signatures. So the catching key generation in the attack part, it's not easy. You don't know when it's going to happen. But secure boot is always happening, sometimes mostly same keys. So we don't do key generation. We are doing the signature generation with different inputs. So that's why we attack signature generation. So we have a couple of places to attack. First, we have expand mask Y. Why I'm saying that Y is attackable, so I will explain later, but it is, as you see, so C, which is public value, is multiplied with S1 and S2. And then this value is generating with addition with value Z, which is signature. So think about it. Z signature, it is equals C multiplied secret key and addition with Y. So if I know Z, which I know, which is signature, is public value, C is also public value. So Z and C I know. If I also extract Y, only thing that I left is S1. So if I don't protect Y, I can also extract S1. So that's why I should also protect Y. I should protect every operation that is including secret keys too. So I'm like explaining which are the part that we can attack for non-profiled and profiled attack. But since I was talking about hardware and the feasibility of non-profiled attack, I will be just focusing on that part. So as we said, there's a multiplication of C and S1, which is C is known. If we know C, we can easily extract S1. And then we have the rejection loop. That can be also profile attack target, also multiplication of this Y. So in our first presentation that was about attack, we attacked this CN-S1 multiplication. So in their implementation, they have two memory. This two memory is holding two different polynomial. One of them is C, the other one is holding S1, and it is one by one feeding this butterfly operation in entity and this multiplication happening. And when we zoom out to this multiplication, so there's like a reduction algorithm also being used. Because we don't want to deal with the numbers that is too high. Because we don't have that much capability in our computer. We have like a 64-bit or 32-bit computing system. So that's why it needs to go through like some reduction parts. So idea is that these two multiplication happen, but the number is too large. We need to reduce it. So that's why they have this like a reduction algorithm. So there's like a Barrett Montgomery, but they use their custom reduction, which is basically splitting in bitwise and working on them and then getting the value. We were targeting the registers because the register is basically CMOS that is consuming the power. And there was like a two register that is visible and then easy to their power analysis. So this is our setup. We have chip sphere, we have FPGA, we have also, so basically this red FPGA is doing encryption signature generation, and the oscilloscope is measuring the power usage. So this is how I collect my power traces. The first line is showing the whole ML-DSA. As you see, I have four like a clear distinguished parts because I was saying that there's a rejection loop. If signature is too big, they are doing the operation one more time. So that's why basically we are saying that the signature rejected 3 times and the last one is accepted. Then I'm zooming it because I want to see which operation happening. So we are calculating the which cycle is entity started. And I zoom in and I see like each, each kind of butterfly operation that like each distinguishable part is basically one entity butterfly operation. Okay, I can clearly see what's happening. Then I can zoom in and I can just attack like even one coefficient. One coefficient, still it is attack that I can see that I extract the secret key. So this is when I zoom in, I was able to see where the multiplication was happening, C and S1. So this is our attack result. We were able to extract the secret key after 10,000 power traces. As you see, the correct secret key has the highest Pearson correlation. So, okay, how to protect them? Okay, we attack, but the idea is that we want to be secure. So that's why we need to add countermeasure. There's a hiding and masking. And the hiding is basically, we want to make sure that this power traces are not distinguishable. So I need to change the order. I need to play with the control path rather than the data path, that I will randomize the coefficient order. So there's a shuffling and WDDL is not a well-known method. Basically, we have AND gate. Let's say that this is using secret operation. They're adding OR gate next to it. They're just giving random values. It is hiding the power usage of this AND gates. So it is basically complementary gates, and it is using the same power usage to hide the information. And masking. So why masking is more important than shuffling? Because there's also many papers that they are still attacking the shuffling, because shuffling can be something that we can overcome. If we can collect more power traces, we can still deal with that. But masking is the only side channel countermeasure method that can be formally verified with some like a mathematical graph methodology. So this is how can shuffling be applied. Okay, I was saying that each coefficient will go through this entity operation. So we can switch the coefficient order before going to entity to challenge the attacker, because the attacker cannot understand which order is being processed right now. This is the idea of shuffling. And then we have masking. So masking is more challenging because we have Boolean operation and arithmetic operation. So Boolean operation, I'm talking about, let's say, XOR or OR operation. But arithmetic operation, where I can talk about addition, where I can talk about AND gate, multiplication, which are more complex. So Boolean masking, let's go over here. Let's say that we have A and B, and we want to protect them, that they can reveal information. And the operation is XOR. XOR B, basically, if they are different, 1, if they are same, it is 0. So random value is R and R1, okay? So we are calculating 2 shares for A and B. So A will have 2 shares, A0 and A1, and B will also have 2 shares, B1 and B0. So I'm using R0 for A, which is A0 is R0. A1 is A XOR R0, and B0 is R1, and B1 B XOR R1. So let's just forget B part, just focus on this part. If I XOR A0 and A1, I will get rid of the R0 and I can still use the A. So I'm just adding other random numbers to hide the actual numbers. So instead of working A and B, I will be working with A0, B0, A1, B1. And it will automatically eliminate R0, but it will have other random values that is hard to distinguish from power traces. This is example. I just wanted to clarify and like also have a proof that is working. So I just want to show A is 4, B is 5. Since I'm working with Boolean, I'm converting in the binary operation. When I XOR them, it is 1. And instead of working with them, I'm using random numbers, R0 and R1. And instead of working with them, A, B, and solid like A and B, I'm adding random numbers and working with them. Still, I have the same input 1. So it didn't change anything, but I just add random numbers. So, okay, this is a good idea. They also think that that's a good idea, and then they apply this protection methodology in Caliptra. So the place that we attack, after they also updated their design and at side channel countermeasure, they add shuffling, as we discussed. They also add masking in the modular reduction circuits that we attack. But it costs 6 times more area overhead. So when I say area overhead, is basically they are comparing the first version of the design and the last version of the design. It was 6 times bigger, which is not an efficient way to add such an countermeasure. So we identify the reason of this overhead, which was coming from reduction circuits, which is it has more Boolean operation that they need to use additional converters. So we show how to analyze and how to find this. So as you see, Adams Bridge itself, ABR, is using like a 200K LUT. Almost more than half is coming from NTT. And the modular reduction, such a small part of the design, is covering 1/3 of the area of LUT in NTT. So it is really big. It is 38 LUT, 38% of LUT, and 47% of flip-flop in NTT engine, which is pretty big. So we identify which operation is causing, which module is causing this overhead. And we design our reduction circuit, which is Barrett. Barrett is basically it has like some division and multiplication operation, but they're expensive in hardware. Again, we want to have something that is cheap. You can implement multiplication in shift, because if you shift right, you are basically dividing by 2. If you are shifting left, you are multiplying by 2. So it means that you can implement this multiplication operation with shifts. So we use shift operation, and we use like a conversion whenever we need to deal with like arithmetic or Boolean operation. And this is our reduction decision unit, like the last part of the design. If it is too big, thank you. We are also doing additional modular reduction units. So we also compare updated version with our methodology. So for the first table, it is showing modular reduction. As you say, LUT was 9,000. We made it 1,200, and flip-flop was 16,000. We made it just 900, and the clock cycle was 157, and we were able to make it only 13 clock cycles. When we integrate this reduction unit, the whole ML-DSA, we visibly also increase LUT flip-flop usage in the whole ML-DSA implementation. It was 9,000 to, I guess this is like a LUT is wrong because it is probably the other version, but I will talk about cycle count for this mistake. But the cycle count, we can say that signature generation was 145,000. And after this, our modification, it was 110,000 clock cycles, which is pretty efficient. So this is our resources. And then I was saying that TVLA. So TVLA is showing whether it is side channel leakage is happening or no. So we tried with different configuration. First plot is showing TVLA result without masking or without shuffling. As you see, it is clearly leaking. It is side channel attackable. And then we added shuffling first. We said that, okay, we don't add masking, but what about just shuffling? And we were able to see that it is still leaking, but it is comparably with the first plot, it is still kind of less leaking. We applied masking and shuffling all together. As you see, the TVLA was below the threshold. That is showing that it is not something that you can attack using side channel attacks. So this is my references, and thank you for listening. That was all. Yes.
Is there any question in the chat?
Yeah, let me see.
Uh,
Okay. Yes, I see. Hello, is the speaker sharing the slides?
Okay. Any questions from the audience? Okay. If not, let's thank the speaker, and we come back after 2 weeks.
Okay,
Okay.
perfect. Thanks so much.
Thank you.
Yeah.